Problem 5 is almost identical to problem 4. In problem 4, we built a confidence interval. In problem 5, we're going to test whether or not there is a difference between male and female support for the president. So that statement highlighted in blue is the alternative hypothesis. The difference in the support for males and females is not equal to 0 if there is a difference between male and female support. Given that this is the alternative hypothesis, the null hypothesis is that the difference is equal to 0. In part B, we're using a 20% level of significance. And we have two critical values. So when you divide 20% by 2, you get 10. And since this is a proportion problem, you can get the z critical values in the infinity row of the t table. So we're going to go to column 0.1 because significance is divided by 2 when you have a two-tailed test. So 20% divided by 2 is 0.1. And the infinity row, the critical values are plus or minus 1.282. The sample proportion for male support or male approval of the president is the ratio of these two numbers. The sample proportion representing female approval of the president is the ratio of these two numbers. I've already copied these numbers into the Excel spreadsheet. So 245 of the 559 males surveyed approve of the president. 239 of the 534 females surveyed approve of the president. The sample proportion is the number of males that approve of the president divided by the sample size. The sample proportion of females who approve of the president is the number that do approve of the president divided by the number of females in the sample. The point estimate of the difference between population proportions is the proportion of males who approve of the president minus the proportion of females who approve of the president. And we're going to copy this to 5 decimal places into Cengage Now. In part D, we need to answer a drop-down menu question. When we're calculating the standard error, the sample proportions are pooled because they are assumed to be equal under the null hypothesis. So under the null hypothesis, if their difference is 0, then the proportion of males equals the proportion of females. And so we're assuming those two things are equal. So P bar for males is a good estimate of that population proportion and that population proportion. P bar for females is a good estimate of this proportion and that proportion. Since the averages of averages is a better estimate than the individual averages, P bar is a better estimate of that proportion and that proportion. Pooling the proportions is actually quite a simple concept. You can think of these males in the survey as being in a pool and these females being in a different pool. When we pool the proportions, all we're doing is we're throwing all females and males into one big swimming pool. So if 559 males were in the locker room and 534 females were in the female locker room, if they all jumped in the same pool, there would be 1,093 people in the swimming pool. Over here, there were 245 males that approved of the president, and there are 239 females that approved of the president. So the total number of people who approved of the president was 484. The pool proportion is just the number of males or females, 44, who approve the president divided by the total number of females and males that are in the swimming pool. So we're going to take this number here and divide it by the total number of people in the survey. Notice that the average of the averages is in between the two averages. The pool proportion is between the male and the female proportions. To compute the standard error, we're going to go ahead and drop the subscript of the variance for the male proportion. We're going to do the same for the female proportion because we're pooling the proportions. So the variance for the male variable is equal to the overall pool proportion times 1 minus the pool proportion. And the same goes for females. So I'm going to copy this and put it down here. So because we're pooling the proportions, the variances of the underlying variables are identical. The variance of the difference in sample proportions is equal to the variance of the underlying male variable divided by the sample size plus the variance of the female underlying variable divided by its sample size. The standard error is just the square root of that. So this is the pool standard error for the differences in sample proportions. We're going to copy this to 6 decimal places and paste it into Cengage now. Next, we need the test statistic to 4 decimal places. The test statistic is just the point estimate of the difference divided by the pool standard error. We're going to copy that into Cengage now. To conclude in part F, we have to compare the test statistic to the 2 critical values. If the test statistic is in between the 2 critical values, then the difference in proportions is insignificant, and we have evidence in support of the null. That is the case. The test statistic is in between plus and minus 1.282. So the null hypothesis cannot be rejected. Thus, we conclude that females and males support the president equally, or the difference in male and female support for the president is insignificant. We're going to check my work and we should get everything correct. And we do.